All right, guys, welcome to the virtual review session on probability. I'm going to do my best to keep this one to a minimum in terms of duration. I just want to comment quickly in the beginning that although binomial and geometric distributions are types of probability distributions that we need to study, I'm going to make separate videos on these. So we're going to start by looking at the formula page that you guys will be working with on the exam. So all these formulas in here, you guys aren't going to have to worry about in this video. Okay. We are going to talk about discrete random variables in this video. All right. So we're going to talk about expected value, which is another way to express the mean of a discrete random variable. And we're going to talk about how to find the standard deviation using your calculator. And then just for our general probability rules, really quickly to go over some notation before we get right into practice problems here. This is an event union, and it means the probability of A or B, okay? And that's always going to be equal to the probability of A plus the probability of B minus the probability of A and B, okay, assuming that these two events are independent, all right? And then we can also look at conditional probability here, right? So this is the probability of A given B, right? So given we already know that B has occurred, what's the probability that event A will occur? And that's going to be equal to the probability of A and B. So this is an event intersection divided by the probability that B will occur. So that's given all the times that B is going to occur, what's the probability that A and B will occur together? Okay, and assuming two events are independent in the numerator here, the probability that A and B happen would be equal to the probability of A times the probability of B. Okay, so we're going to work with these formulas. We're going to work with the addition rule, which is for or statements, and we're going to work with the multiplication rule as well, which is for and statements. Okay, so moving quickly on here, just really quickly to think about a Venn diagram, because sometimes they'll even show you a Venn diagram on the exam. We can think about event unions and intersections like the following picture, right? So imagine, right, the area in this oval is going to represent the probability that event A can happen. The area in this oval is going to represent the probability that event B can happen, right? So the area in the outside is going to represent the area that neither A nor B happen. And the shaded area in the middle is going to represent the probability that both A and B happen, right? And if you think about probability in terms of this picture here, you can kind of understand the formulas, right? If I want the probability of A or B, right, I want this area here, right? But when I add these two probabilities together, I'm going to count this shaded overlap region twice, right? As part of event A and also as part of event B, right? So when you add the probability of A and B together, you've calculated or you've double counted this middle space, which is why when you look at the formula, we have to subtract it out at the end when we're dealing with or statements. Okay, and then likewise, for and statements down here, right? You just need to multiply the independent probabilities together, okay, to get the area of this overlap region. So with that, we're going to hop right into some practice questions, okay? So this is using a two-way table. They'll often ask, some basic probability questions using a two-way table. Okay, so here it says in the table above, what is the probability of A and E occurring, and what is the probability of C occurring given that E has already occurred? All right, and They usually ask one or two of these. These are ones that we really should be successful with. They're pretty easy. You don't have to worry about formulas really with a question like this out of a two-way table. Okay, so the probability of A and E occurring, right? If there's 125 units in this table, right? I have my E column here. I have my A row here. So I'm looking at the intersection of those row and column. And I see there are 12 units in this box, 12 out of 125 total units in the table. And that's the probability that both A and E will occur at the same time. Okay. And then if I'm thinking about the probability that C will occur, given that we already know E has occurred, right? So now we're just going to focus on the E column, right? Because I'm saying I already know E has occurred. It looks like E is going to occur 63 times. So out of those 63 times, right, what's the probability that C also occurs? Well, C also occurs 28 times when E has already occurred, right? So I can go through now and look for where do I see 12 out of 25? So I can cross off that, and I can cross off that, and then where do I see 28 out of 63? It's got to be answer choice C. Okay. Cruising along here, we have the tree diagram, which is also very handy for probability. I really like using tree diagrams specifically for conditional probability questions. If you can build a tree diagram with the information that they give you for a conditional probability question, I often find that it makes it easier. But specifically, if they're going to give us a tree diagram, we might as well make use of it, right? So they're asking us the probability of B given X. Okay, you have the formula sheet on the exam. So go to your formula sheet and here is your conditional probability formula, right? They're telling us the probability of A given B is equal to A and B divided by B, right? So let me write that on this question, right? And then I'll show you how to put it to use, right? So the probability of A given B is equal to the probability that A and B occur divided by the probability that B occurs. Okay? But they're not asking us about A and B, they're asking us about B and X. So really all I have to do is rewrite this formula in terms of, or rewrite this formula over here in terms of B and X, and I'll be able to figure out what I'm supposed to do with this tree diagram, right? So instead of A and B, we're dealing with B and X. So the numerator is going to be the probability that both B and X happen. And the denominator, right, is just going to be the probability that X happens. That's the conditional piece. The conditional piece is we're saying, what's the probability of A given B has already occurred? So we're going to say, what's the probability that we get event B given we know that event X is going to happen, right? Because in this case, event X actually comes second, but that's okay, right? So first thing I have to do now is find out, well, what's the probability that that X is going to occur, right? And that's going to be my denominator, right? The probability that X occurs. Okay, that's the whole that we're measuring out of because we're saying given that X is going to occur. So in order to do that, I'm just going to do some simple probability calculations on my tree diagram. X can occur two ways, right? It can occur when A has happened first, or it can occur when B has happened first. So if I want the probability that A and X will happen, I'm going to do 0.8 times 0.3. 0.8 times 0.3, and I'm going to get 0.24. Right, so here's a 0.24. And then the other way that X can occur would be if B happens first, and that's going to happen 20% of the time, and then half of that 20% of the time, X will then occur after B has occurred. So 0.2 times 0.5 is going to be 0.10. right? So the probability that X is going to occur is going to be, well, this probability here plus this probability of here. Those are all the ways that X can occur. So X is going to occur 34% of the time total, right? I can calculate a probability for A then Y, A then Z, B then Y, B then Z, but those are all the outcomes, and these are the two that have X. So 34% of the time, X is going to occur. Now, given that we know X is going to occur, what's the probability that B occurs? Well, if B is going to occur after X, or if B is going to occur before X, but they're both going to happen, we must be talking about this pathway, which is why it says the probability of B and X in the numerator, right? So we're talking about 20% of 0.5, or 0.2 times 0.5. 0.2 times 0.5 gives me 0.1. So we're looking at 0.10 out of 0.34, which is not a fraction that they give us here. So I'm going to do 0.10 divided by 0.34. I'll use my calculator. I'll hit math, fraction, and I see we're going to get 5/17. So it has to be B. Okay. Let's keep it moving here. This one says, it turns out that 25 seniors at Random High School took both the AP Statistics exam and the AP Spanish Language exam. The mean score on the statistics exam was, for 25 seniors, was 2.4 with a standard deviation of 0.6. And on the Spanish language, it was 2.65 with a standard deviation of 0.55. We want to combine these scores into a single score. What are the correct mean and standard deviation for the combined scores? So here's the problem with this question. The answer is actually E. You can't determine the standard deviation because they don't tell us here that these are independent events, and I can only use the standard deviation formula when I know that I have independent events. And because these two exams are happening for the same 25 seniors, and that's the data that we're adding together, right? We're doing, your score on the AP exam plus your score on the Spanish language exam, right? We're not going to be able to figure out what the combined standard deviation is, because you can only use that when you know that you have independence. All right. So I really don't love this question. If for some reason they said that they were independent, okay, or this answer choice here wasn't an option, and I knew I had to find a standard deviation for the combined distribution. But first of all, let's just touch on the mean. You'll notice all the answers are the same for the mean. And that's because if I'm adding everybody's AP score in statistics, I should put an S there, AP statistics plus AP Spanish language, then the means of the combined data set are just going to be the old means from the individual distributions added together, right? So 2.65 on the Spanish language plus a 2.4 in statistics would give you a 5.05. That would be the average score if you combined everybody's scores together. Okay. And then if we did know that there was independence, okay, they do give you the standard deviations of the individual data sets. If you're asked to combine a data set and you need to calculate the standard deviation, okay, you take the individual standard deviations. So in this case, the standard deviation from AP Stats, and you square it so that you can add it to the standard deviation for Spanish language. Okay, I also have to square that. Remember, I can't add standard deviations, but I can add variances. And if I take the square root, I turn them back into a usable standard deviation. I think if you actually try to do it For this question, you get 0.81. So that's kind of a trap answer because they want you to say that you need independence. I don't love this question, and generally you can't determine the answer is usually not an answer choice on an exam. In my experience, it's usually not the correct one, but in this case it is. Okay. Moving on, the GPA of students who take AP statistics exams are approximately normally distributed with a mean of 3.4 and a standard deviation of 0.3. Using table A, we're not going to use table A. What is the probability that a student selected at random from this group has a GPA lower than 3? Okay, sometimes they give you some easy, normal distribution questions, all right, to satisfy some, continuous random variable probability questions. All right, so this is a slam dunk for us, right? We know this distribution is centered at 3.4. Okay, they want to know what's the probability of randomly selecting somebody who has a GPA of 3.0 or left. So 3.0 would be to the left of 3.4. And they want the area to the left of that. They give us a standard deviation of 0.3. So quickly, I can hit second distribution, and I can do normal CDF, right? And I'm going to leave the lower boundary as negative 1E99 on a continuous distribution. I'm trying to give the lowest number possible. The upper boundary is going to be 3 on a distribution that's centered at 3.4 with a standard deviation of 0.3. And I'm going to get 0.091. Okay, and we get 0.0912. The closest answer to that here is 0.0918, and they say they generated this answer using the table. Okay, so obviously we use the calculator, so the answer is slightly different, right? The calculator is going to be better. Okay, so that's how I knew that this guy had to be the answer. It had to be A. All right. Then we want to look at the one underneath. Okay, the one underneath, the 2000 census identified the ethnic breakdown of the state of California as approximately 46% white, 32% Latino, 11% Asian, 7% Black, and 4% other. Assuming that these are mutually exclusive categories, and this is not a realistic assumption, what is the probability that a randomly selected person from the state of California is of Asian or Latino descent? So this is important, right? This mutually exclusive thing, right? Mutually exclusive, again, means that they can't occur at the same time. So basically, for this group of people in California, when they categorized you by race, you could only go into one category. All right. So they basically didn't allow you to count towards two ethnicities as mixed, right? They're basically saying that everybody can get one classification. Okay. And it says here, this is not a realistic assumption because that's not the world we live in. But statistically, it's important, right? Because for mutually exclusive events, the probability of A or B is just equal to the sum of the probability of A plus the probability of B. We don't have to worry about subtracting out the overlap, right? We don't want if this was out of 100 people, right? And were we talking about? The probability of Asian or Latino, right? So imagine if 11 out of 100 people were Asian plus 32 out of 100 people were Latino, right? But if they were allowing us to count people in both categories, right? And let's say maybe I had 4 people who were both Asian and Latino, right? I would have counted those 4 people in each of these categories, and I would have to subtract them out at the end, right? And that's what our formula sheet tells us. But since they tell us these events are mutually exclusive and that they can't occur at the same time, I don't have to worry about subtracting anything out because there is no overlap. So I simply need to add the probability that I am Asian, which in this case is 11%, plus the probability that I'm Latino, which in this case is 32%. And I will get the probability that I am one or the other, and that's going to be 0.43. So this one's D. Okay. Moving right along here again. This time it says the students in problem 4 were normally distributed with a mean of 3.4 and a standard deviation of 0.3. This is referring back to the same question that we did a couple back. They're saying in order to be in the honor society, you must have a GPA that's in the top 5%. And then they say out to 2 decimal places, what's the minimum GPA we must have to qualify for the honor society? So again, it's the same distribution, but it's a different question. All right. They tell us we're dealing with a normal distribution centered at 3.4. They tell us again the standard deviation is 0.3, except this time instead of, in the other question, they gave us a cutoff. They said, what's the probability of choosing someone who has less than a 3.0, right? And to find that area, we did normal CDF. But that's not what they're asking this time. This time they're saying, what does our score have to be? So they're not giving us a score. They're giving us an area. What does our score have to be to register in the top 5%? Okay, and that's not a normal CDF function. That's the inverse norm function, right? So I'm going to hit second distribution, and I'm going to go to inverse norm. Okay, and I'm going to say, all right, the area to the left of this cutoff point is going to need to be 95% if the area to the right is 5. All right, and now if I just hit paste, my calculator would give me the z-score needed to be in the top 95%. And then I could manually, algebraically figure out what this score has to be then by using the z-score formula and modifying, taking the z-score, multiplying it by the standard deviation and saying, all right, adding that to my center point, my mean, and that would give me the cutoff. But I don't need to worry about that if the calculator can do it for me, right? So I'll tell the calculator I'm working on a distribution that centers at 3.4 with a spread of 0.3. And it's going to give me the cutoff manually, right? So instead of me having to say, all right, I need to be, 1.5 standard deviations above average, and then figuring out what score that is on the graph, I just plugged it in, calculator did it for me. And out to 2 decimals, we're 3.89, right? So it's got to be E. All right, moving on. Let's see. This one says the following are probability distributions for 2 randomly selected variables, X and Y. And then it says if X and Y are independent, what is the probability that X is 5 and Y is 4? So first of all, they're telling us they're independent. And for 2 events that are independent, if you want to know an and probability, what's the probability that X is 5 and Y is 4? All I have to do is multiply. So what's the probability that X equals 5 times the probability that Y equals 4? Now they give us the probability that X equals 5. It's 1/2, right? So I can plug that in right here. Oops. As 0.5, right? 1/2 and 0.5 are the same thing, times. And the issue is they don't give us the probability that Y equals 4, but they do give us all the other possibilities and their probabilities. So I can figure out what this is because every probability distribution needs to add up to 1 or 100%, right? So if I just open up my calculator and I figure out, well, what are all these other what do all these other pieces add up to, right? So if you think about it, actually, we can probably do this in our head if we just deal with fractions, right? This is a 16 down here. So how about I turn this into 16ths, right? This would be 2/16, and I can turn this one into 16ths as well. 6/16, right? So now if everything's out of 16ths, and I have 2 and 6 is 8, and another 3 is 11, right? So if I do 1 minus 11/16, I should have 5/16 left over. Of course, you could have done all that in your calculator too. Okay, if you didn't want to do the fraction math in your head, you could have just did 1 minus 1/8 and then subtracted 3/8 and then subtracted 3/16. And then if your calculator gave you a decimal, you could have hit math fraction and you would have gotten to the same 5/16 that I got to. Okay. All right. Let's see here. Wait, hold on. Did I do something wrong? Oh, geez. I did do something wrong. Oh my gosh. 5/16 is the right probability for y equals 4, but I forgot to come back to the beginning and multiply them together, right? So that was silly. I knew I was missing something here because it shouldn't have been a, right? So I did all that to find the probability that y equals 4, right? But then I forgot what the question was asking. What's the probability that x equals 5 and y equals 4? So you could plug this into your calculator, but 0.5 or 1/2, right? Just don't think about it in terms of a decimal. I should have left it as a fraction, right? 1/2 times 5/16 is going to be 5 out of 32. 5 out of 32. So it should have been C. My bad. Here, we're doing some expected value in this question. All right. They're asking you if you were to bet $1, what would be your expected return, right? Especially if you see that word expected, you know they're talking about expected value, right? And this is also, whenever you hear expected value, it's really the same thing as finding the mean of a discrete random variable, right? Look at the values that this variable can take, right? It can take on the value -1, which is losing $1. It can take on the value +1, which is winning $1, or it can take on the value +2, which is winning $2. Okay, and there are no outcomes in between here, so this is not a continuous random variable. It's discrete, and if you come back to your formula sheet at the beginning, right, there's your formula. Add up the product of all the outcomes and their associated probabilities. That's all this says. Okay, so I'm going to come back out here to slide 9. All right, and I'm going to do that, right? So if there is a 60% chance that I am going to lose $1, to that, this is the expected value, okay? I am going to add together the sum of each outcome and its associated probability. So losing $1, 60%, we're going to have a 25% chance of winning $1, and then we're going to have a 15% chance of winning $2. Okay, and if you plug this all into your calculator, I think it's going to come out, if I remember correctly, to be -5 cents. Okay, right? 60% of the time you'll lose $1. 25% of the time you'll win $1, 15% of the time you'll win $2. Okay, but if you were to play this game over and over and over and over and over and over and over again, you're going to lose $1 the majority of the time. And so these smaller chances of winning $1 or $2 aren't going to be enough to overcome that. And in the long run, you'll always, you can expect to be down about 5 cents on average over many, many plays per turn. Okay. Next, this is, let's see, you own an unusual die. 3 faces are marked with an X, 2 faces are marked with a Y, and 1 face is marked with a Z. What is the probability of at least one of the first 2 rolls being a Y, right? So basically they want the probability that my first roll is a Y plus the probability that my second roll is a Y, right? And I only need, really, I should say, it's just at least, right? So all the outcomes that satisfy at least, right? What are the different outcomes of at least one, right? Getting 1 Y satisfies it, or getting 2 Ys satisfies it. What doesn't satisfy at least 1 Y would be getting 0 Ys. So to make it easy on yourself, just figure out the probability that the person doesn't roll any Ys. And if you subtract that out from 1, you'll get the probability that they have at least 1 Y, right? So let's just figure out what's the probability that you don't roll a Y, right? So 3 faces have an X, 2 faces have a Y, and 1 face has a Z. So that's 6 total faces. 2 of them have a Y, which means 4 of them don't. So here's your probability that you don't roll a Y, okay? So the probability that I don't roll a Y twice would be 4 out of 6 times 4 out of 6. And this is the only condition that doesn't satisfy, right, at least 1 out of 2. If you're going to roll a dice 2 times, you can get 0 Ys, you can get 1, you can get 2. This is the only one that doesn't satisfy that. So I'm finding that probability, and I'm going to subtract it from 1, and it will leave me with the other 2. Okay? So 1 minus, this is really going to end up being 1 minus 16 out of 36. So we can do that in our calculator, right? 1 minus 16 out of 36. And that's going to leave us with this decimal. We'll just hit math fraction, and we get 5/9, which is an answer here. Answer choice D. Okay. This one says you roll 2 6-sided regular die. What is the probability that the sum is going to be a 6, given that we're going to get a 4 as at least 1? So this one's really tricky to try and do by hand. So if it was me on the exam, and it won't take you long, I would draw out a sample space. Okay, so here's one die. 1, 2, 3, 4, 5, 6. Here's the other die. 1, 2, 3, 4, 5, 6. And then all the spaces on the inside, are the sums, right? 1 plus 1 is 2. 2 plus 1 is 3, right? So these are all the sums if you rolled any of these numbers on the outside, right? Now they told us, we're going to say, given that we know one of the die is a 4. So here are all the boxes where one die is a 4, right? Here's my 4. And all these boxes in here, all the sums are including this 4. But we also have to worry about the other die, which could also be a 4, right? So given that one of these is a 4, I'm outlining in red all the sums here that have one of these dies having a 4, okay? And so where are all the places where we get a total of 6, right? There's only 2 spots, right? You have to roll a 4 and a 2 in order to get a sum of a 6, right? There's more than one way to get a sum of a 6, but if one of the die has to be a 4, okay, then the other one must have to be a 2, right? And when you're rolling 2 die, there are 2 different ways you can roll a 4 and a 2 and get a 6, right? Your first die can get you 4, and the second die can be a 2, and that'll get you 6. Or your first die can be a 2, and your second one can be a 4, and that'll get you 6, right? So there are 2 ways that it can happen. But remember, we said given that one of them is a 4. So there are only 1, 2, 3, 4, 5, 6, 7, 8. Don't count the 8 twice. 9, 10, 11. There are only 11 total ways to roll a dice and have at least one of them be a 4. Okay, I have highlighted all those possibilities, and 2 of those possibilities have a sum of a 6. So your answer should have been 2 out of 11. Okay, draw yourself a sample space if you have to. That will help. All right. Quickly, I'm going to do a couple short answer questions, and then we're going to cut it off here. All right. So this one asks you to find the mean and the standard deviation for a discrete probability distribution. Okay. This really isn't bad. The calculator will do it for you. You could use expected value formula, right? Multiply all these together and then add them up to get the mean, but the standard deviation is tougher. They also give you that formula on your formula sheet, but there's really no need to use it because the calculator will do it for you, right? So I'm gonna hit stat, edit, and you can see I already plugged these into my list, right? So I have 2, 3, and 4, and then their probabilities. I put them in as fractions, but the calculator automatically converted them to decimals. So then I'm just going to hit stat calc, one variable stats, and you'll notice my frequency list, I made an update. Normally when you run one variable stats, okay, you just have one list with the outcomes. But since these outcomes are associated with different probabilities, and I put those in L2, you're going to want to make sure you hit second list. And you're going to want to make sure you tell the calculator the frequencies are in L2. So that was not my default. Okay, the default, when I hit stat calc, one variable stats, generally this space will be blank. So just hit second list and put it in there. Anyway, I can hit calculate here. It'll give me the mean. There's the mean, 2.9166666. There's your standard deviation right there, 0.759. All right, and that is what I would write on my exam if I was asked to do this. Okay, let's see, a couple more. Let's see. Okay, so the first piece is saying, given that the probability of A is 0.6 and the probability of B is 0.3, and the probability of B given A is 0.5, they want us to find the following. Okay, so let's see, right? For A and B, remember, we're going to want to do the probability that A occurs times the probability that B occurs given A has occurred, right? Because they don't tell us these are independent. If they were independent, I could just do the probability of A times the probability of B. But since they give me the probability of B given A, and they tell me it's 0.5. If these were independent, right, I could just multiply them together, 0.6 times 0.3. 0.6 times 0.3. When two events are independent, you can just multiply their probabilities. So if two events happen, right, if one has a 60% chance and another has a 30% chance, and these two things have no effect on each other, occurring or not occurring, right, then they're only going to overlap 18% of the time. But they tell us here they're going to overlap 50% of the time. So are these events independent? No. We already know that, actually, just by doing some quick math. They can't be independent. Okay. Then what else, right? So the probability of A and B, well, they give us the probability of A is 0.6, and the probability that B will occur given A occurred is 50% of the time. So this is going to come out, I'm going to be off the screen here, but that's going to come out to be 0.30. Okay. And then the probability of A or B, right, that's going to be A plus B minus the probability that they both occurred. Okay. So let's see. We would have to do 0.6 plus 0.3 minus the probability of A and B. What did I say? Oh yeah, we already figured that out, right? So minus the 0.3 for the probability that they both occur, right? And that's going to leave us with 0.6, right? 0.6 plus 0.3 minus 0.3 is going to leave us with 0.6. So that's the probability that one or the other occurs, right? One plus these two probabilities added minus the probability that they both occur. All right. We also could have proved that they're not independent just because, right? Remember the definition of independence? I guess I kind of took the long way to prove it, and I didn't need to do that much work, right? The probability that B occurs is 0.30, but that probability changes if we know that A has already occurred, right? So by default, these have to be dependent on one another, right? The probability should not increase. If they're independent, the probability that B occurs would not increase if I already knew that A occurred. So they can't be independent, right? I proved it a different way, but that one's easier. Okay, let's see. Let's try and finish this out here, right? They say consider a set of scores of 9,000 scores that are normally distributed with a mean of 500 and a standard deviation of 90. What is the probability that a randomly selected score is greater than 600? This is easy, right? We do this in our sleep now. Normal CDF, the center of my distribution is at 500. What do they want? A score greater than 600, right? So you're going to do normal CDF, lower boundary 600, upper boundary 1E99, use a mean of 500, a standard deviation of 90, and you have your area. Same thing here. Change your lower boundary to 450 and your upper boundary to 600. All right. And then we reviewed this already, right? What does Ralph need to be in the top 1%? Again, that's not a normal CDF job. That's an inverse norm, right? They want to know what's the cutoff for the top one. Go to inverse norm. Tell the calculator you need the cutoff for 99% area to the left. Tell the calculator the mean and the standard deviation. It will give you the cutoff. All right, so let's finish with this last guy. It says consider two discrete independent, so that's important, random variables x and y. The mean of x is 3. The variance of x is 1, right? They give you the squared, so you know it's variance, not standard deviation. They give us the mean of y is 5. The standard deviation of y is 1.3. It says find the new mean and the new standard deviation if we subtract all the numbers in the data set. Okay? If we take this variable x and then we take variable y and we subtract all their values, right? What will the new combined distribution look like? So the means are just going to be subtracted, okay? So we're just going to take the means that they gave us and subtract them, right? The mean of x minus y is going to equal the mean of x minus the mean of y. They gave us the mean of x as 3 minus the mean of y is 5. So on a combined distribution, the center point would be at -2. Okay, and then we'll finish off with finding the new standard deviation. Remember, standard deviation, or I shouldn't say standard deviation, variances, right? You can't add standard deviations together, but variances always add. It does not matter how you combine your random variables. You can add them all together. You can subtract them all apart. Okay, either way, the variability in the distribution is getting bigger. But remember, you can't just add standard deviations together. You got to add variances first. Luckily for us, they gave us these as variances, right? So they gave us 1 and 1.3, right? So I don't need to square them. They're already squared. Those were standard deviations that got squared and turned into 1 and 1.3, right? And then if I want to turn them back into standard deviations, I'll take the square root. So I need the square root of 2.3. And what is that going to come out to be? I think if you plug it into your calculator, it's going to come out to be 1.52. And that's it, folks. 46 minutes, not bad. We reviewed so many probability questions, all right? You can rewatch them if I was going too fast, but I was doing my best to keep the time on these down, all right? So I will see you guys tomorrow.